Hello everyone. Today we will start the class with the CAN details of CAN network, which is called as controller area network. This particular protocol was developed way back in 1986 by a company from Germany called Robert Bosch. Um, this particular protocol is used in the automotive industry at an extensive level, wherein different uh, issues that are there in the vehicle, they are connected to the CAN line and they exchange the information between themselves using the controller area network. So why basically we are using CAN in the automotive industry? There are multiple reasons for that, but before getting into the details, try understanding what would happen if the CAN network was not there. So in the absence of the CAN protocol, the diagram on the screen shows the different configuration that we are having to connect the ECUs. Now, the ECUs that are there in the car, like engine control ECU, transmission control, active suspension, anti-lock braking systems, they all are connected via a central unit called as dashboard. Now, the problem with this particular configuration is there are multiple lines or wires which are going from one ECU to the another. And secondly, if the centralized ECU for some reason goes faulty, then all of these ECUs are not able to communicate to each other. So there are two major problems with this kind of configuration or any other configuration that you will see in the absence of CAN line is that there are multiple wires going from one ECU to the other ECU. So the cost of wiring increases. And secondly, when there are so many wires floating in the network, then obviously the EMI and EMC magnetic interference and the magnetic field that is created by the uh, flowing voltage on different wires also increases. So that could also lead to the corruption of data when the data is flowing in. And secondly, when there is central ECU connected to all the other ECUs, then obviously there is a lot of dependency on this central ECU to be working correctly. If for any reason the central ECU is not working, then none of these ECUs, other ECUs, would be able to talk to each other and convey the information. So those are the major drawbacks of the topologies for wiring when the CAN was not invented. Okay. So without CAN, as you see in the screen, we have written increasing number of ECUs. Then there was a lot of direct point-to-point communication. And then because there are multiple wirings, the EMC would be on the higher side. And there's a lot of extra wires that are used. So this is one of the topologies that is commonly used. With this, you can also have mesh setup, matrix setup, star topology. But all those would probably have one kind of issues or the other. So going back to why we are using CAN and how is the CAN line resolving these problems. So now in the diagram that is shared on the screen, you will see that the obviously at the first instance you will see that this is much more planned and it seems much more aesthetic, right? So there is only central lines which are called as high speed and low speed CAN, and each of the ECUs they are connected to a high speed or low speed CAN using a single, actually a dual wire. But the number of wires that are there in this particular diagram, they are much more lesser than the previous diagram. So that is why CAN uses much lesser wiring than compared to the other wiring topologies that we have. Here in the diagram, you are seeing CAN high and CAN low, right? CAN high and CAN low are basically the different configurations of the CAN line. So you would notice that CAN can work up to 1 Mbps and the length of the CAN wire shouldn't be more than 40 meters. How we are deriving that 40 meters would be discussed later in the course. So high speed CAN that we are seeing, all the issues that are very critical to the functionality of the vehicle, they are connected to high speed network. What are the ECUs which are connected to high speed network? They are transmission control and anti-lock braking system, active suspension, and engine controllers. So these ECUs need information from other ECUs at a very high speed, right? Because if you see, anti-lock braking system is nothing but the braking module. If the time taken to react on a braking event is more than fractions of second, then somebody could lose their life. Okay, so anywhere in the car, when the information has to be uh, communicated at a very high speed, or the results could be disastrous or catastrophic, then they have to be connected to high speed CAN line. On the low speed CAN line is basically for issues like power steering or lightning or infotainment. Okay, so here if you see, low speed can work at 256 or 5 and 2 kbps. Here in these issues, you will notice that even if there is a small delay, like if you switch on the AC and let's say the AC starts after 500 milliseconds, then in that case nobody is dying, right? Nobody is like getting a discomfort uh, because of that minute delay. So all those issues which are not hard embedded, in other terminology, which are soft embedded, that means there could be a little variation in the output. Those are connected to low speed CAN. And then the central ECU, which is called again the dashboard here, as the previous example, is having two CAN lines. One is connected to high speed, another is connected to low speed, and in both the cases they would be working in independence. So if the low speed is not working correctly, it will not affect the high speed. Here the dashboard is basically taking high speed signals or messages on one CAN line and connecting or translating those data into a low speed CAN line. If there is a need from any of the ECUs to have communication or information from the other CAN line. So that is the work done by the dashboard ECU, which is also sometimes called as gateway ECUs. Okay, so this is how the CAN line is configured. So why we are using CAN in automotive is because it is simple. As you will see, this diagram also is very plain white and simple. And there are ECUs which can be plugged and play. That means any of these ECUs which are connected on the CAN line, they can be removed or they can be added without really affecting the network. So if you see the previous configuration or previous diagram here, even if you remove the dashboard, all of these ECUs will stop working. Any of these will stop working because they are connected to each other through dashboard ECU. Okay, so that can be avoided. Here, each and every ECU can be removed or added to the network without affecting the other ECU. So it is a very plug and play kind of configuration. The number of ECUs can be removed or added without really affecting the other ECU or the network. And then there are a lot of inbuilt error detection mechanisms that are present in the network, in the CAN line. What are those inbuilt error detection mechanisms would be discussed in the later slides. And the CAN line is very robust, and the speed of the CAN line is also high. So as I said earlier, it can vary from 1 Mbps maximum, starting with 250 kbps, and there are different configurations that are supported by CAN line. So this is why the CAN is preferred over other protocols. Now let's see about the CAN features in much more detail. So if you really see, CAN is basically a twisted pair cable wiring mechanism. What does it mean? This means that there are two wires which are known as CAN high and CAN low, and they are twisted with each other. And there is a termination resistor of 120 ohms placed at the end of the CAN lines. So why this 120 is derived? This is basically based on the inductance that is created by the wiring harness assuming the maximum length of the wiring in a CAN line is 40 ohms, 40 meters. So based on that, this 120 ohms is derived. Another use of termination is that it also controls the bouncing back of the signal at the termination. Okay, so that is the effect of but that is the need of 120 ohm resistance. So if you see in these nodes, there are basically three nodes shown on the CAN network. Both of them or all of them have a microcontroller. Then there is an inbuilt CAN controller in the microcontroller, and then the CAN controller is connected to a transceiver. Okay, and that the transceiver is having a CAN high and a CAN low line connected to that, and inside the transceiver there is an arrow which is going up and the other arrow is going down. So these lines are called as TX and RX. Okay, so if you really differentiate the functionality of a CAN controller, the CAN controller is inbuilt into the microcontroller, which takes care of forming the CAN messages, then doing the error checking, and accepting or rejecting the messages, and all other functionalities related to CAN protocol is done by the CAN controller. So ultimately, there is also a need of a hardware which converts your digital data into a voltage on the CAN line, right? So that conversion of digital data into electrical signal is done by the CAN transceiver. So if you see, all the ECUs are having a transceiver, and then the CAN controller and the microcontroller. So the microcontroller is basically having the application which wants to transmit the data to a different ECU on the CAN line, and those data are basically in the form of messages. The formation of the messages is done by the CAN controller. The CAN controller is responsible for formation of the messages, doing the inbuilt error detection, then acceptance of the data, acceptance of the messages, then sending of the messages, receiving of the messages, and all the driver level software is kind of controlling the CAN controller. CAN transceivers are basically nothing but devices or electronic components which are receiving and doing transmission of the CAN messages. Basically, they are taking the digital data and converting that into a electrical signal on the CAN line. So what are the other properties of the CAN protocol which are extensively used in automotive? So first of all, it is a multi-master protocol, and then it is also a broadcasting protocol. So let's see what is multi-master. As multi-master word signifies, multi means many and master means the master nodes. Okay, so literally it means that any of these ECU in this particular picture, node 1, node 2, node 3, any of these ECUs can become master at different time of transmission. So there is an inbuilt mechanism so that if more than one node tries to send messages at the same time on the CAN line, okay, then there is a method called arbitration through which one of the nodes becomes the master of the bus, and it gets the access to the bus and able to transmit the messages. So any node can become master at different instance of time, and it can hold the bus and ready send its data on the bus. So that is why it is called as multi-master. And broadcast means it is very similar to the broadcast group that we have on our WhatsApp. If you are sending the messages, it will go to everybody who is connected or included in the broadcast group. So that means if the node 1 is trying to send a message to the node 2, then with node 2, node 3 and other nodes that are connected to the CAN line, they will also receive the message. And after receiving the message, they would decide whether they want to use the data or not. So it is a broadcasting mechanism. That means once the node puts a message into the CAN line, then any of the nodes or all of the nodes would receive it. Okay, and after reception they would decide whether they really want to use the data or not. That is up to the application. So it is multi-master broadcasting. And then it is an asynchronous communication. Communication means there are two types of communication basically, right? Asynchronous and synchronous communication. So synchronous communication needs a third party signal that is synchronizing the transmitter and a receiver. So there are many serial communication protocols like I2C, SPI, where you have MOSI, MISO kind of configuration, master in slave out and slave in master out, right? So all those configurations are synchronous configuration, because ultimately they are using a different third party or third signal, which is called as clock, and based on the clock the message is flowing. So in CAN there is no synchronization mechanism from node to node. There are other synchronization mechanisms that are implemented, but they are not using any external clock or external signal for synchronization. That is why it is called as asynchronous communication. And this is called as, it is a serial communication and half duplex. Half duplex means the transmission and reception cannot happen at the same time. Means either the node would be sending or receiving. Okay, so half duplex means it is controlled by one node, and that node is transmitting data onto the bus. And the third property of the CAN line is differential two wired bus. So what is the meaning of differential two wired bus? Let me explain this using this particular slide. Now this is one of the configurations of a CAN line, which is having a differential voltage. And as it was mentioned here, that it is a differential two wired bus. So here, as I've seen in the diagram also, there is a CAN high bus and there is a CAN low bus, right? So these CAN high and CAN low are available at a different voltage level. So recessive bit, which is basically a digital one on the CAN line, is represented by a difference of absolute zero between the CAN high and the CAN low. And a dominant bit, which is a digital zero, is represented by a differential voltage of 2 volts between the CAN high and CAN low. So the CAN high is always present at 3.5 volts, and the CAN low is present at 1.4 volts. And depending on the absolute difference on the CAN high and CAN low, the recessive and dominant bit is predicted. So what is the advantage of having two differential voltage levels on the different wires? Let's suppose there is a noise which interrupts both of these CAN high and CAN low, and let's say the noise value in digital signal is minus 0.5 volts. So 3.5 minus point would be 3, and 1.5 minus point would be 1. So difference between 1 and 3 would be 2 again. So that way the absolute difference between the signals always remains the same, and that is how the correction of data is ignored, because is protected. If as let me repeat again, if there is a noise that is coming on the CAN line, it affects both the CAN and high and the CAN low, and that is why the absolute difference between the two wires, the CAN high and CAN low, during the recessive and during the dominant, remains the same, and that is why it is noise protection. The EMI EMC protection is very high in CAN. So that is the meaning of differential two wired bus. And this is a message based protocol. So every information that is flowing from one CAN node to the other CAN node is message based. That means all the information is packed into a message. Each message has a message identifier, and based on the identifier there is a priority of the message link, and with that priority the node will win the bus, and the node with highest message priority or lowest identifier would be able to transmit on the bus. So that is how the arbitration takes place. Arbitration is a philosophy or a protocol through which the access to the node is given to a particular access of the wire is given to particular node. So that is called message based. Error checking and fault confinement. So error checking mechanisms will be explained later. There are different error checking mechanisms. Fault confinement means, the literal meaning of confinement is that it is restricted to itself. That means suppose something goes wrong in can high. Suppose something goes wrong in one of these nodes, then the node would restrict those errors to itself. That means it will shut down itself and it will not affect the other nodes that are connected on the canvas. So that is confined. The fault is confined to the node in which it is existing, and it will not disturb the bus, neither it will disturb the other CAN nodes that are connected in the network. So that is the meaning of fault confinement. And error checking, we will discuss in the later slides. Okay. So I think this I have already explained, and now let's talk about the CAN frame. So as we discussed earlier in the previous slides, all of the messages or the information in the CAN line flows through CAN messages. Okay. And what is the shape or the format of a CAN message is what we are trying to see here. So a standard CAN frame would basically have these many sections as listed in the diagram. So everything start with the start of frame, which is a recessive bit. Recessive means start of frame is a dominant bit which means a digital 0, and recessive means digital 1. So here you need to understand very important mechanism that CAN uses a wire and logic. Okay, a wire and logic. What is the meaning? The meaning is that let's suppose there are two nodes which are transmitting at the same time on the canvas. Okay, in that conflict, what will be the voltage level of the bus is decided by the wired and logic. That means if there are two nodes, both of them are transmitting 0, then on the bus the actual value would be 0. If there are two nodes which are transmitting 1 on the bus, then the actual voltage level on the bus would be 1. If there are two nodes which are transmitting 1 and 0, one is transmitting 1, the other is transmitting 0, then if you add 1 and 0, you will get 0. Okay, so that means 0 would be there on the bus, and same 0 or 1, then also 0 would be there on the bus. So it uses a wire and logic to resolve the conflict between the nodes and really decide the voltage level of the bus when there are more than one node sending data of different polarity on the bus. Okay, so just to come back to the CAN frame, this is basically a data frame, and I'll tell you what data frame and remote frame is later. But try to understand this particular formatting. So the frame start with the start of frame, which is common to all the frames. Start of frame is basically one bit of data, which is a dominant bit. Dominant means it is a 0, digital 0. Okay. Then it is followed by the identifier field, which is arbitration field, also called as message identifier, message ID, and it is 11-bit identifier. In CAN, there are two different kinds of identifiers applicable. One is called as 11-bit identifier, and the other is 29-bit identifier. So I'll explain later what is 29-bit identifier, but basically you need 11 bits to represent any identifier or message name or number in the CAN frame. Okay, and that is the 11-bit identifier. Then there is a bit called RTR. RTR is called as remote remote transmit request. So this particular bit is a 1 bit data. In the data frame, which I'll explain you later, it would be a dominant, and in a remote frame, it will be 1. Okay. Then ID is ID bit is a dominant bit, and then there is a reserved bit which is also kept as dominant. This ID, E, and RTR plays a important role in deciding the priority of a message when we have uh, messages on the same line of different message length, identifier length. So there is 29-bit identifier, there is 11-bit identifier, and both of them can coexist coexist on the same CAN line. So there, when we have two different kinds of identifier lengths transmitting data on the same CAN line, then this RTR and ID bit plays a major role. So this is the remote, and then DLC. DLC is basically your length of the data. Okay, so that is 4 bits. So the maximum length of the data that you can have in CAN frame is 0 to 8 bytes. So 8 can be represented in 4 bits only. That is why the DLC has 4-bit size. And if you want to suppose your data frame has only 4 bytes, then you will have representation of digital binary 4 in DLC. So these 4 bits are basically signifying number of bytes that are present in data field. After that, there is a 15-bit CRC sequence, okay, and one bit delimiter. So what is CRC sequence? CRC sequence is nothing but it is used for representing and showing the integrity of the data. Okay, what do you mean by integrity of the data? Let's suppose there is a transmission of the data from the sender to the receiver. Okay, and let's assume that sender is sending 10 and the receiver is not receiving 10, but the receiving node is receiving 11. Okay, so how would the receiving node know that this 11 was the intended data or 10 was the intended data? Okay, because whatever the receiver is able to receive, it might assume that this was the data that was intended to be sent by the transmitter. But during the transmission, there was a corruption of data and 10 became 11, right? So those kind of corruption of data cannot be detected if there is no integrity check on the data during the transmission. So how is this CRC, which is called a cyclic redundancy sequence, which is a 15-bit of data, helping in this kind of scenario? So in this kind of scenarios, what is happening is that the transmitter, let's suppose it is trying to transmit 10, it will transmit this 10 through a CRC polynomial and generate a 15-bit CRC. Okay, so when the receiver receives the data, in let's say it is receiving 11, it is passed the 11 to the same CRC polynomial, which is controlled by the CAN protocol. So all the CAN controller are using the same CRC sequence. Okay, CRC, not sequence, the CRC polynomial. So even the 11 is passed through the same CRC polynomial, then whatever the transmitter was has sent will not match with what receiver has produced. Okay, let me explain this again. When the transmitter is sending the data, let's say the data was 10. Okay, with that data would be written, 10 would be written into the data field. It will be transmitted on the CAN line, and with that, the transmitter will also transmit the CRC sequence of 15 bits. So how is CRC sequence generated? CRC sequence is generated when the data, in our case, which is 10, is passed through a CRC polynomial and it generates a 15-bit CRC sequence. So that CRC sequence is appended to the data and passed to the receiver in the CAN frame. The receiver, let's suppose instead of 10, it receives 11. Okay, if it receives 11, it passes 11 through the same CRC polynomial and again generates a CRC sequence. But now this CRC sequence that is generated by the receiver will not be same as the CRC sequence which was sent by the transmitter. In that case, this message would be rejected. Why it would be rejected? Because the receiver knows that something has gone wrong during the transmission, and the data that I have received is not correct, and that is when the receiver rejects the CAN frame, and that particular error is called as CRC error. Okay, so that is how the integrity of the data is maintained. The next bit that you are seeing is the delimiter. Is basically a recessive bit, which is kind of giving an extra cushion or processing time for the CRC to be calculated, to be compared with the receiving CRC, and decide whether the message has to be rejected or transmit or accepted. So the acknowledgement field, the next field is the acknowledgement field, which is again one bit of size. The acknowledgement field is is sent as one by the transmitter, and when any of the nodes on the CAN line uh, receives the message successfully, then it converts that one into zero. Okay, it basically converts the recessive bit to a dominant bit, and um, that is when acknowledgement is given by the receiver. So you would also know that every node that is sending on the CAN line is also receiving the same bit by a feedback looping mechanism. So when the transmitter sees that in the acknowledgement bit it sent a 1, but it has received a 0 because somebody else has made that recessive bit to a dominant bit. That means the transmitter gets a signal that somebody is able to some one of the node is able to receive the message correctly, and that is when it will understand the frame is successfully transmitted. So even if one node is able to give a successful uh, signal for successful reception, then that transmission would be considered as successful transmission. So the receiving side makes the acknowledgement bit from 1 to 0, and again it is followed by a delimiter, which is again a recessive bit, which gives an extra cushion or time for the voltage level to be made from 1 to 0, and it should be sensed by the other ECUs on the CAN line. Okay, so after that there is an end of frame, which is again 6 recessive bit, but we can check in the document. That is the end of frame, which marks the end of the standard frame. So to summarize, we start with the start of frame, then we have an identifier, RTR bit, ID, recessive reserve bit, then DLC of 4 bits, data field 0 to 8 bytes, CRC 15 bits, delimiter 1 bit, acknowledgement again 1 bit, delimiter again 1 bit, and then end of frame is, I think it is 6 recessive bits. We can check in the document. So this is how the sequence of the CAN frame. So maybe I'll also explain what are the different types of frames before we come back to the process of arbitration. Now in the different types of CAN messages. So the frame that I just explained is a data frame. What is a data frame? Data frame is basically a message that is sending, or that is having the data which is transmitted from one transmitter to the receiver. Okay, and mostly the data in an automotive environment, they are cyclic messages. Other than the diagnostic messages, all the messages are cyclic messages. That means the information from one node to other node is cyclically transmitted at every particular instance of time, and mostly those instances 20 or 50 milliseconds. So what I'm trying to say here is that in data frame, any frame in which the data is going from one node to the other node is called a data frame. And in data frame, the RTR bit, which is just beside the identifier, the RTR bit, which is called a remote transmit request, is always dominant. Okay, so a data frame would have a RTR bit as dominant, and a remote frame, what is the meaning? Remote frame is basically a frame that is requesting data from some other frame, okay, some other node. That is remote frame. So remote frame would have the RTR bit as 1, and there would be no DLC or data field in the RTR in the remote frame. What is the meaning? Since remote frame is requesting for a message, let's suppose there is a node A and node B. Now, node A is needing some data from node B, and that is when it will send a remote frame to the node B without any DLC or without any data. As soon as the node B sees the remote frame from node A, it will understand that the node A is needing some data, and then it will send a data frame with whatever the data it is trying to send, which can vary from 0 to 8 bytes, to the node A, where the RTR bit would be 0. Okay, so a remote frame are basically a request for the data, and data frame are the frames which have the actual data. Okay, error frame and overloaded frame would be explained later, but just to give you an idea, overloaded frames are the frames which are used or sent between regular messages to provide some extra processing time for the nodes, so that they are able to digest the information, store it, and probably come back and receive the upcoming data. So a overloaded frame are basically a an extra time or frame that is sent to get an extra time during the regular transmission and reception, so that the data that is received is properly stored and digested. Okay, yeah. So I think the sequence of the messages would be clear to you, and the next important concept is about the arbitration. Okay, so what is the meaning of arbitration? So arbitration um, basically means the process um, by which we decide which nodes gets the access to the CAN line. Okay, so that is called arbitration. Here in CAN, we basically have two different kind of arbitration. One is called as CSMA by CD, collision sense multiple access by collision detection, and then CSMA by CA, collision sense multiple access by collision avoidance. Okay, so here the arbitration is a mechanism, is a method by which we are able to define the priority of the message, and also give the access of the CAN line to a particular ECU. Okay, so why do we need this arbitration? Because CAN is a multi-master protocol. Each and every node can become the master, but how would that be decided? Which node will take the precedence? Which message would be given the priority? So that is decided by the arbitration. Okay, there are two ways of doing arbitration. As I said, CSMA by CD, which is collision sense multiple access by CD. CD means collision detection. That means the nodes will start transmitting, and during the transmission, the priority of the message would be decided, and the and who gets the access is decided, right? And the other is CSMA by CA. So is CSMA by CA is collision avoidance. Now in CAN, we use CSMA by CD, but it is good to understand what is CSMA by CA. In CSMA by CA, it's basically a mechanism in which you don't wait for the collision to occur. You have a preset pattern in which the nodes would be transmitting, and no two nodes will overlap the transmission of each other. What do I mean by that? Let's suppose an example in which there are 6 nodes which are trying to transmit. Okay, and every node would be given, let's say in an hour, every node would be given 10 minutes in which that particular node will transmit, and after the 10 minutes are over, then the second node will transmit, and after 10 minutes the third node will transmit, and it will go on till the sixth node has transmitted in the whole 1 hour. So each and every node has their specific timing in which the node would be transmitting the messages. Nobody can transmit the message out of their timing. Okay, so that way the collision is avoided. But the problem with this kind of configuration is that suppose there is a node which doesn't have anything to transmit, but in that case, also the 10 minutes that are assigned to that particular node, no other node would attempt to transmit. And that is why there is a lot of wastage of resources and time. Okay, so and that is why this CA is not preferred in automotive industry, because we are wasting a lot of time. And since the data is very critical, and the speed of transmission and reception is also very high, collision avoidance is not applicable to automotive industry. Okay. What is applicable to automotive industry is CSMA by CD, which is used by the CAN protocol. Here, let's suppose there are 6 nodes which are trying to transmit the data at the same time. Okay. Now, depending on the arbitration or the identifier that I showed you, 11-bit identifier or 29-bit identifier, the priority of the message would be decided. Okay. And based on the priority of the message, the highest priority message would be keep on transmitting, and that particular node will get the command of the CAN line, and it will continue to transmit. Okay, so how is the priority of the messages decided? In a nutshell, we can say that the lower the decimal value, the higher the priority. Okay, lower the decimal value, higher the priority. So how exactly is that taking place in the CAN line is shown in this particular picture. Let me expand this for clear vision. Okay. So now here I am showing you an example in which there are node 1, 2 and 3 which are having a 11-bit identifier, and then each of these 11-bit identifier, there are different identifier or message IDs which the node 1, 2 and 3 are transmitting. So what node 1 and node 2 and node, what these red lines are signifying is basically a 11-bit representation of that identifier number. Okay, this red line that is marked for node 1, node 2, node 3 is basically 11-bit representation of their message identifier. Let's say for example the identifier number is 8. Then what is the binary representation in 8 bits? It will be 4 zeros followed by a 1 and then 3 zeros. So if you want to make it into 11 bit.
Something I found on the web. According to lulusosa.com, it is a fertilizer which stimulates heavy breathing.
Okay, so what I was saying is that let's suppose we have an identifier which is represented in 8 bits. Let's say the identifier number is 8. So 8 would be 4 zeros followed by 1 and then followed by 3 zeros. If I want to represent that in 11-bit identifier, then I'll add another 3 zeros to the MSB, and then it will become 11-bit identifier. The same way, node 1, node 2, node 3 are having 3 different identifiers represented by a red line. Okay. And then, as I said, when there are different voltage levels or different data that is transmitted during the arbitration field onto the CAN line, then a wired AND logic is used to really hold the voltage level of the bus. So if the node are transmitting 0, 0, then bus will have 0. If the nodes are transmitting 1, 0, then the node will have 0. And if the nodes are transmitting 1, 1, then the node will have 1. So the last or at the bottom, there is a bus state which is having CAN high and CAN low. And based on wired AND logic, what will be the resultant bus level of the CAN line is represented in the red. Okay, so start of frame is basically the first bit is the start of frame, which is a dominant bit, since all of the node 1, node 2, node 3 are having start of frame. They will be dominant and the bus state would be dominant. right? The 10th bit is recessive for all. The 9th bit is recessive for all. The first time, uh, the first time when there is a conflict between the data that is sent by the different node is the is the bit 5. Okay. Before that, what happens when the node are transmitting 0, and since everybody is 0, it will receive 0. So all the nodes thinks that they are getting the access to the CAN line. So if there is a node which sends 0 and receives 0 on the CAN bus, then it will keep on sending transmitting the data. But suppose if there is a node which sends 1, but on the bus it receives 0, then the node understands that there is a higher priority message being sent by a different node, and that is when that node becomes receive only. Okay. So if you see 10th, 9th, 8th, 7th, 6th bit here, whatever the node is sending, all the three nodes, and they are getting the same thing back on the CAN line. So if they are sending dominant, they are receiving dominant. If they are sending recessive, they are receiving recessive on the CAN line. So that is the time whatever they send, they are receiving the same back, and that is why they know that they are winning the arbitration, and they keep on sending. Now the first time the conflict happens is at the node 5. The node 1 has a dominant, the node 2 has a recessive, and the node 3 has a again dominant. So a dominant and recessive when on one sent at the same time on the bus will have a dominant based on the wire and logic. So the node 0 sends a 0, receives a 0, that is why it will continue to send. Node 2 sends 1, receives 0, that is when it understands that somebody is sending another higher priority message, and from that point it becomes receive only. Okay. So once it becomes receive only or listen only, it will not attempt to further transmit the message and wait for the end of frame to happen. And then after end of the frame, at the start of the frame, it will start transmitting the, when there is a bus idle, it will again start making an attempt to transmit the message. Okay. And since the node 3 is having a dominant, it again receives a dominant on the bus, and it will continue to transmit. Okay. So after node, on the node 2, after bit 5 will only be listen only. The next time the conflict occurs, it is at the node 2, bit 2. Node 1 is transmitting a recessive, which is 1, and the node 3 is transmitting a dominant. So 1 and 0, a wired and logic, it will become dominant on the bus, right? When it is dominant, then the node 3 will continue to transmit, and node 1 will become listen only. So after that, the node 1 will not further attempt to transmit and will be only listen only till the end of the frame. And then as soon as the end of frame is received, there will be a bus idle state, and after that it will re-attempt to transmit the message again. So at the first time of the arbitration, there would be three nodes fighting. Once the one node wins, it completes the message. The next time there would be two nodes fighting, and then one will win, and at the last there would be after both of them are transmitted, the last node will transmit. So that is how the arbitration takes place. Okay. So this is a very important logic of how the priority of the messages is decided in the CAN line, and how it is how the CAN is able to decide which node will take the precedence on the CAN network. So this is CSMA by CD logic. Yeah. Okay. So I think for this class we will stop here. The further concept will be covered in the next class.